So here we're going to look at vector valued functions. For example, R of t is a vector, t is a real number. When we plug a real number in, what is the result? So the first example we will look at is R of t is 2 cos t in the I direction plus 3 sine t in the j direction, or times j. And the other way we can write that is R of t is 2 cos t, comma 3 sine t. So I could plug in some values. For example, what is R of 0? If I plug in 0, what is the vector that results? 2 times cosine of 0 would be 2. 3 times sine of 0 would be 0. How about R of pi over 2? That would be 2 times cos pi over 2, 2 times 0. 3 times sine pi over 2 would be 8 times 1 is 3. But again, we can do this for all values t. My domain, in essence, is the set of all real numbers. But I may want to restrict this for the sake of my discussion. So let's say I want to choose values between 0 and 2 pi. So examine this function, this vector valued function R of t. And I prefer to use this notation. 2 cos t, 3 sine t, for t in the interval from 0 to 2 pi. And what we're going to do is we're going to go ahead and construct a graph of sorts. And I'll show you two of the points on the graph. When t is 0, we are at the point 2, 0 here. And when t is pi over 2, we're at the point 0, 3 here. So what is that going to look like? What is our picture going to be for this? So I've actually programmed a spreadsheet to show us some values. So let's take a look at that. So my vector valued function is 2 cos t, comma 3 sine t. And I wanted 0 to 2 pi, so I'm going up by 1/10. From 0 going up by 1/10, and you'll see we have all of these points. And 2 pi is about what? 6.28, so 6.2, 6.3. So we get this far. So we have all of those values. Again, notice I started at 0, 2, 0 is what we saw. And 0, 3 pi over 2 is about what 1.57. So in this range, then you can see we're getting close to 0, 3. But then I graphed all of these points. Now, in essence, each one of these represents a vector. Yes. So let's go ahead and construct that graph again. And here it is. And you'll notice there's the point 2, 0. There's the point 0, 3. And this, each point represents a vector starting at 0, 0. And we graph all of the terminal points to go ahead and show us the path of this vector valued function. But what can we say about this? So yes, it is an ellipse, of course. R of t is the position function. R prime of t is the same as v of t, which is the velocity function. And R double prime of t, which would be v prime of t, is a of t, or the acceleration function. So if we're looking at our example here, we can certainly construct the velocity and the acceleration from our R of t. So what do we have here? We have R of t equals 2 cos t, comma 3 sine t. Velocity v of t is r prime of t, which would be -2 sine t, comma 3 cos t. And the acceleration, a of t, which is our double prime of t, or the velocity's derivative, will give me -2 cos t and -3 sine t. So this example is in 2 dimensions. We can certainly have a 3-dimensional vector valued function as well. So let's take a look at one of those. What if I had r of t is 2 cos t, 3 sine t, and then 0.2 t. So what's happening here? So we still have the ellipse happening in this direction, but then the z keeps growing as t is changing. So as t goes from 0 to larger numbers, the t gets larger, so the z gets larger. So what do you think that's going to look like? What will that image of that graph be? So we try to build in the geometry of these concepts. So let's take a look at that. So here's our graph in 3 dimensions. Can you see how it's working? We get this helix that is making one full turn from 0 to 6.3, so just about 0 to 2 pi, and then it's crawling up to that level. Now, if we look at it in 2 dimensions, that's what we had before. That's ignoring the z. Notice that's our same ellipse as we had before, x out to 2 and -2, y up to 3 and -3. Once I go to 3D, we see that the z value is causing that to grow, and we're able to construct this helix. If we want to get it running a few more times, we certainly can do that too. We just change where we're ranging from. Maybe I can go from -10 to 10 on my t values, and you'll see this is going to go. And we see what we have. Now, the animation there is a normal vector and a velocity vector, unit normal, unit tangent. We'll talk about those as we go. But you can see as I change that from -10 to 10 on my t values, I get that helix turning multiple times and growing as we go. Notice some of it is below the z-axis because my t's were negative, t from -10 to 10. Okay, so that gives you an idea what that looks like. Can we get the velocity and the acceleration of this thing? So again, the velocity v of t would be -2 sine t, 3 cos t, 0.2, and the acceleration of t would be -2 cos t, -3 sine t, and 0. So for this helix in the z direction, the acceleration is just 0. So let's look at how we would write a vector valued function for a line. So let's say I have the point P is 2, 4, 3, and I have the point Q is 5, -2, 9. What would my vector valued function be? Well, it's essentially the same thing as getting the equation of the line in parametric form. Recall, we could say x of t equals y of t equals z of t equals. We're starting at 2, 4, 3. To get from 2 to 5 is up 3, so that was plus 3t. From 4 to -2 is down 6, so that's minus 6t. And from 3 to 9 is up 6, that's plus 6t. So this is in parametric form, but how do we convert that to a vector valued function form? We again say r of t is what? R of t is 2 plus 3t, 4 minus 6t, 3 plus 6t. Can we get the velocity and acceleration from this? Of course, velocity is just the first derivative. velocity v of t would be 3, -6, 6, and the acceleration, the derivative of velocity, what is the acceleration going to be? 0, 0, 0.